First of all, we have a continuous transfer function, we have a continuous controller, and if you remember, we have our controller, and then we have our zero order hold, and then we have our plan, JS it's called now, okay? And so the idea here is to make the analysis, everything in continuous time. In the previous session, we did it in discrete time. Now we want to do it in continuous time. So we found the equivalent system. Let's say this equivalent system, so it's just an approximation. Let's call it J of S, whatever. Okay, which will be the equivalent system, including the zero order hold, making the hypothesis that the exponential term can be linearized. Okay. And then we found out Kc for a given phase margin in continuous time. So just continuous time analysis. And after that, the obvious things to do is to discretize our controller with these three methods. So remember this backward different method. I can just go through once of them once again, just to remember what we were doing. So we have our controller in continuous time. We know what Kc is. We found it was 0.7 something. The first method is this one. It's the backward difference. So backward difference, we just approximate with, it's like equivalent to approximating a derivative with a first order difference equation. Okay. So basically it's more or less the same as saying like a derivative, or let's call it differently. I cannot clear it. The underlying idea that this is more or less equal to kt minus y k minus 1 t divided by the sample time. Okay, this is the underlying idea. It's not exactly this, but it's the idea behind this method. And so we end up with a discretized controller or discretized transfer function in general that remains stable. So here stable part is located here. But as you can see, there is a lot of distortions. For example, we don't have any poles in this region here. And so that means that some poles are kind of overlapping in this, or not overlapping, but shifted inside this smaller circle than the unit circle. So strong distortions can appear and stability is preserved. And there's also the same number of zeros and poles. So here I got 1 0 and 1 pole. And so I end up with 1 0 and 1 pole. This is always true. Same number of poles and zero in discretized model than in the continuous model. Then we've quickly seen this second method with the testing method. Here we're just, the underlying idea is to kind of make it an integral as a finite sum of elements, whatever. You can look at it in the lecture notes. And indeed, we find that for this one, all the poles, once again, were stable in continuous time, remain stable in discrete time here. But this time we have a mapping is mapping to all the unit circle. So we also have all of the stability limits that remain at the stability limits here around or on the unit circle. So we will have, probably we can have some ringing effects with this method. Remember that backward difference, it's not really possible to have ringing because everything is mapped between a unit circle or half a unit circle center at 0.5. So no poles are close to -1. Here we will have poles to close to -1. Or it's possible, but still there's some distortion. So I'm going to show that also at the end of this exercise, but here you can draw the so-called Nyquist frequencies, okay? And you see that there's a problem is that if you get infinitely large frequency, they will just all map here. So they will all go here, okay? So if a pole is really, really fast in terms of or infinitely large in the S-plane in the imaginary part, so poles that are located there and there, so conjugate pair of poles, then this pole will be mapped really close to -1, and this can result to ringing. Why did that so? It's just because on a discrete, on the discrete planes, on the plane on the right here, remember that this will be equivalent to the amplitude here, the distance here, and then this angle here, if I can take two conjugate pair of pole, correspond to the equivalent of the frequency. And so if I have a really large frequency, then this angle is maximum. So it's close to being on the real axis on the left hand side, so real negative value, but it's never reaching the real axis. In this case, it's just getting really close. So the poles will got really close here. So this is for the Tustin method, which is probably the most the one that you use most of the time, or you will use most of the time. And finally, remember, it's match pole zero method. Here it's a little bit different. We just take all the poles and all the zeros, and we directly discretize them with the definition of the Z transform. So Z is equal to exponential ST. And we found out that we also need to add the infinite or non-finite zero. So here we have 1, 0, 1 pole, so there's no problem. But if I have a function with 2 poles and 1, 0, I need to add another 0 at -1. It's how the method is designed. You can see it's written here. And then we need to match the gain. So to match the gain, we need to define where the discretized version should have the same gain as the continuous version. In other words, if we decide that the discretized version should have the same gains at really low frequency or really high frequency, then we're using this static gate at equivalent to a high pass filter or low pass filter, depending on the transfer function. And if we want to match it at one particular, one specific frequency, it's also possible. So here, remember, we just first do it as a high pass filter. So we try to match the frequencies for infinitely large frequency. And here on the right, we try to match the gain for omega equals 0.1, because in our continuous analysis, we defined that at omega equals 0.1, we want to have we have the margin that was 45 degrees, if I remember well. So we have we have identified the transfer function in continuous time for the controller, so that there's something special happening at omega equals 0.1, and we want to keep that true in discrete time, or almost equivalent in discrete time. And so here's the first remarks with that. In MATLAB, when you use this method, usually MATLAB prefers to end up with strictly causal transfer function. So I don't know if you know exactly what it means. So I'm just going to go through this example. Hopefully it's not the case here, because why is it not opening? Okay, so it's not happening here because here we have only 1 pole and 1, 0. So when you discretize everything, you would directly end up with 1 pole and 1, 0. But I just wanted to show you an example here. So I just defined a transfer function. So this will be my system. So I have 1, 0 and 3 poles in this case. By the way, can you all see the MATLAB? I guess you can all see the MATLAB now. So I have 1, 0, and 3 poles. And if I discretized it with MATLAB directly, I end up with a system that has only 2 zeros and 3 poles. And in the method we've just seen, we always need to include all the zeros at infinity, and here MATLAB is only including 1. So if I compute it analytically, so as is it in the lecture note, then I will end up with this here. So we'll have the initial system in continuous time that shows 1, 0, so 1, 0 and 3 poles. And then I know that I should always end up with 3 zeros and 3 poles in discrete time, because here it's equivalent to plus 2 zeros at plus minus infinity, infinity times j, whatever. And so if I directly use MATLAB, I end up with only 2 zeros and 3 poles. And here is the method that's proposed in the lecture notes, 3 zeros and 3 poles. So obviously the zeros are discretized, sorry. Zeros discretized here is the same as the one here, and the denominator is exactly the same, obviously because the discretization is the same. But here in the lecture note, we should include 2 zeros at infinity, so 2 zeros at -1, whereas MATLAB is only including 1. And so here you can see that this transfer function here, or this one, the one from MATLAB, is what's called strictly causal. And this one here, it's just causal. So what it means is that in this transfer function here, remember that I can put all the denominator on the left and keep the numerator on the right. So I can end up with y times, here, let's say it's a second order. So I got z3 plus something, this second and so on, is equal to u time, and I've got only z square. So d square plus something times z plus and so on, okay? And I can just rewrite this equation as y of k plus 3, or something times y of k plus 3, let's call it. So usually it's 1. Here it's always, yeah, it's always 1 because of how we've written it, but never mind. You can call it alpha 3, for example, plus alpha 2 times y of k plus 2, and so on, will be equal to, let's call it beta 2 only, u of k plus 2, plus beta 1, u of k plus 1, and so on, okay? And so if we rewrite this, we can see that y of k plus 3, okay, is a function of previous version of y here, and only previous version of u. So the current control inputs will not affect the current output, okay? This is what strictly causal means. In the causal case here, if I make the same analysis, I will end up with ak plus 3 plus previous version of y should be equal to u k plus 3 plus previous version of u, okay? Obviously with some coefficient here. Okay, so this is the difference. And if we plot this, so let's plot this now, you will immediately understand what I'm talking about. So you have in blue the continuous line. Let me just find the magnifier here. So in blue, it's the original system. So here it's just the step response I'm making. Yeah, I'm just making a step response in continuous time in blue, and then a step response in discrete time with the 2 version. The dark orange one is from the MATLAB one, so strictly causal system. And the yellow one is a non-strictly causal system, just causal system. And as you can see, the dark orange one from MATLAB is never happening before the blue curve, whereas the yellow one is like on top of the yellow curve, and sometimes it's kind of before, okay? So for example, if I take this point here, you see that I'm reaching, can probably do it in MATLAB directly here. So if I'm looking, for example, at this point here, I'm reaching the amplitude 3.24 after 3 seconds, whereas for the continuous time, this same amplitude is only reached at 3.45 seconds, so 0.45 second later, okay? This is because it's not strictly causal. And if you discretize it with strictly causal, if you end up with a strictly causal discrete version, then you can see that this amplitude is reached at 4 seconds. It's even later, okay? This is a main difference in MATLAB. There is various reasons underlying why MATLAB prefers to do it strictly causal if possible. But it's just to remind you that MATLAB is computing it a little bit differently. So sometimes the results can be a little bit different. Okay, so is there any question regarding this three method to discretize the controller? If there's no, we're now obviously going to look at a unit step response in Simulink. So here it is how it looks like. We're going to do it in MATLAB, so it's going to be easier to see what's happening.
I just wanted to ask if there is some advantage of how MATLAB is doing the transfer function.
So yeah, as I've just said, if I just rerun the code here, you see that they are quite close to one another. The only main difference I can see here is that if you want to implement, for example, the controller, then having a strictly causal method usually means, for example, if you're, I mean, you should all know what a state space model is. So you got like X, let's put it in continuous time. That doesn't change anything. You will have X dot is equal to AX plus BU, and you have Y is equal to CX. This is a normal form. This is only possible if it's strictly causal. If it's not strictly causal, I will have a d times u here. And this here means that it's not strictly causal if d is not 0. So this is mostly the only difference. Then you can also look at which signal is better at approximating the blue line. And here, I mean, some will say the yellow one is better, some will say the orange one is better. I mean, if you discretize it here with quite a large sampling time, then it cannot match exactly the blue line. So it's just up to you if you prefer having something that can little bit shifted on the left or on the right. But there is no obvious, there's no method better than another one. I mean, it's really depending how you're going to use it and what you need it for. Okay.
Okay, perfect. Thank you.
So this was what we did. So here I just created the system. We already did it last time. Then we create all the, we find the phase margin, or we find the gain to fulfill the exact phase margin. We've also seen that. And then we discretize the controller. So to discretize the controller, first you define the plant here in continuous time. Then you can define the plant, the controller, sorry, in continuous time as well with Kc found before. So it should be 0.7. It's found with the phase margin here. Then you define the sampling time, you define the Z variable. And finally, you can define, as is it in the PowerPoint. So here it's just the controller discretized with a backward difference testing, pole zero matching with high pass filters, so matching the gain at infinite frequency, matching the gain at a pulsation in radian per second of 0.1, okay? And then you can also ask MATLAB to discretize, okay? First of all, we're gonna have a look at what MATLAB did compared to what we did. So for the testing method, it's exactly the same. You can look here, it's the same gain, it's the same discretization for pole and zeros, obviously, but mostly the same gains. And if we look at how MATLAB discretized everything in, or using the match pole and zeros method here, we cannot specify for MATLAB where to match the gain, okay? So here we end up with 3 different systems. The first one here, cannot see it properly. Here it's matching the gain at infinity. Here it's matching the gain at 0.1 radian per second. And here it's matching the gain at what MATLAB decides, okay? So anyway, what you should remember is that the poles and zeros are exactly the same because it's exponential ST, no problem. But the gain can be slightly different. You see here it's 10.9, 10.884, 10.897, okay? So most of the time it's okay, you can use whatever you want, especially if you're, I guess MATLAB is more or less always matching the gain at infinite frequency or 0 frequency. If you have only a bandpass filter, I don't really know how it matches the gain, but you can still do it manually. Here, the only things to remember is that it's pretty close from one another in our example. And now the goal obviously is to find the step response. So for finding the step response, I just switched to Simulink. I don't know if all of you have already used Simulink before. Just very quickly, we've got our reference step input. So it's a step at 0. So it just starts right at the simulation start. Then you have a step. This will be our input. If we focus on the first branch here, we have the continuous controller that we define. Okay, so this controller is the one that we define in continuous time. So there's the Kc gain that we find times, I don't remember what it was like 15S plus 1 over S, something like this, time this 0.703, which comes from the Kc we found. So this is our continuous controller and the continuous plant. Okay, so this will be the kind of reference we want to follow, but using a discrete controller. So then the second branch here, this one, we implement the discrete controller with the Tustin method. So it's just the Tustin, the discretized controller we got here with this transfer function here. And we end up our zero order hold block. Zero order hold with the frequency or the sampling time Ts that is defined. That exactly is the same sampling time as the controller, by the way. So here already we could have, I mean, this block here in Simulink, as is it coded here, it's completely useless because this is discrete, there's already a zero order hole at the end. So here it's just a kind of duplication just for make it clear for everyone that there is a zero order hole, but it is not useful here. And then we have our continuous plant, okay? And of course, I forgot to mention it, but we always have our feedback loop. And we do that for the discrete testing method, first it's the backward difference method, then it's a discrete testing method, and then our two method for our two different controllers using this pole zero matching or match pole zero method, okay? So if we run this and then look at the results back in MATLAB, because it's easier to see what's happening. So just a little bit of plotting. Here you can see the results. So on top, you got the plant output. The reference is the blue one. The one that we want to follow is the continuous one, and it's, yeah, the continuous one is the blue one. What is happening? They use 2 times the same color. Okay, never mind. So the one we want to follow is the blue one. It's not the one that won. Okay, it's one that is already inside here. You see the blue one in the middle. And we can also look at the controller output. So the controlled inputs, if you want the discretized control inputs, and compare it to the continuous time input. So you can see that the discrete input is a little bit different than the continuous input. It's always the case because of the discretization of the controller is not perfect. It doesn't exist. I mean, you cannot have a perfect following of the input, and you want to follow the output. So obviously the input can be shifted a little bit in discrete time. And here the only main remark I can make for this particular system is that as the sampling time is quite small, you can see that if I unzoom, the sampling time is, it's okay to use a discrete controller with this kind of sampling time for this plant. If you go back to the lecture note, you have some rule of thumbs to find how small should be the sampling time with respect to the plant main frequencies, natural frequencies. And here it's perfectly fine. So all of these methods to discretize the controller will lead pretty much to the same input control and to the same output, okay? So here, I mean, we can study the output, say, for example, the orange signal has a little bit more damped oscillation. So the backward difference is damping a little bit the system here. Can say that, I don't know, in terms of rising time, the best one is the Tustin method, and the backward difference is a little bit slower. That's probably why it's a little bit more damped. But yeah, I mean, there's nothing, all of these controller here will perfectly fit our needs, okay? Is there any question regarding this discretization of a continuous controller and then the implementation? If there's no question right now, let's go to the first question of today, and probably you will have some questions thereafter. So this first question, you're given a controller in continuous time and a plant in continuous time. So exactly what we did, okay? You assume that the controller design is made so that the closed loops is stable. So someone just designed JC of S so that the closed loop are stable. Can be to fulfill some kind of phase margin as we did, or pole placement, whatever, we don't care. We just know that in continuous time, JC times JS in closed loop is stable. And now we want to, of course, discretize the controller. So first, discretizing the controller with matched pole zero mapping method brings no frequency distortion, only the gain may change. Second proposition is that after discretizing the controller, it is always mandatory to check the closed loop stability in discrete time. Third one is with the matched pole zero mapping method, two distinct continuous poles can result in two discrete poles at the same location. So that means that if in my controller, I've got, for example, two poles at -1 and -2, then when I discretize this controller, I can end up with two same pole or two poles located at the same location in the discrete plane, okay? And the last one is with the Tustin method, the high frequency poles and zeros are always removed because of the exponential approximation. So exponential approximation will just kind of remove all the poles that are too fast. Here, of course, worth to mention it because it's not mentioned, but here we assume that already in JC times JS, okay, so we design JC already knowing that there's a zero order pole. Okay, so the analysis is made already with the zero order, exactly as we did. In the results, most of you, most of you, but only 43% of the people who answered the poll said that the third one is correct. Okay. And so that was true. The question is, why is it correct and why the other one are not? So first, we're going to investigate the first one. Discretizing the controller with matched pole zero mapping method brings no frequency distortion. We've already seen that this is not possible. Just a simple example, if I've got a controller, okay, takes the pain. So if I got a controller like this is equal to 1/s plus 100, for example, okay, and I've got a sampling time of 1 second, then you can see that here's a problem because 100 is really much faster than the sampling time. So I will never be able to design something that will be almost equivalent, okay? And this will be true for all the discretizing method here, including the matched pole zero mapping method. Then if we look at the second proposition, so after discretizing the controller, it is always mandatory to check the closed loop stability. This is always wrong, assuming that, and it's not written, but I just said it, that here already we consider J of S times H of S with H being zero order whole, and we assume that the sampling time is chosen so that it's sufficiently small to capture all the plant dynamics and the controller dynamics. Under these assumptions, we've seen that the the method we found to discretize the continuous controller will always ensure that the poles will stay in the, if a pole is stable, then it will remain stable, okay? So it's not mandatory to check the stability under the assumption that the sampling time is small enough, okay? If we look at the first one, so with the testing method, the high frequency poles zeros are removed. This is completely wrong. We're also going to look at this where we will talk about aliasing, but mainly you have to remember that in testing method, wherever I am in the S plane, okay, when I mapped it to the Z plane, I will always end up here. So if I've got a frequency, for example, here, then I will probably map it there, let's say. And if I got a really, really high, so I mean, it's not frequency here, it's zero frequency. But if I start increasing in frequency like that, then I will probably go here. So on a smaller circle. And then if I go further higher in frequency, I will further go here. Okay, but my pole will always exist in the Z plane. Okay, it's if I've got two poles in the S plane, I will end up with two poles in the Z plane. So there is no kind of canceling, removal, or whatever. And if I've got infinitely fast pole, which doesn't exist, I mean, it has to be finite, but never mind, then they would just meet almost at -1. So here, not -1 because it's not on the imaginary axis, but it will be here somewhere. Okay, so really close to the real axis with the negative value. And indeed, the last one was with the matched pole zero mapping method, two distinct continuous poles can result in two discrete poles. And so this is really important to remember that if I'm in the S plane and then in the Z plane, we've seen that with the matched pole and zero method, if I have a pole, for example, let's take an imaginary pole, it's going to be much easier. So if I have a pair of poles there, okay, they will be mapped somewhere in Z. I'm going to do it analytically, it's going to be easier. So if I've got Z equals plus or minus I, for example, then we know that this will be mapped to exponential st. So if t is equal to 1, let's say for a simplification, then it will be equal to S plus or minus I, okay? And to this will be mapped at, it's probably not the best example I took here. Let's say it's I over 2. It's going to be better. Oh no, is it going to be better? Never mind, let's take I. Should work the same. So here plus or minus I, that means that in the Z plane, exponential. So here it's S. So in the S plane, I've got plus or minus I. In the Z plane, or approximately, I have exponential plus or minus I, okay? Which is -1 or -1, okay? Now if I take S equals plus or minus I plus or minus plus 2 pi I, for example, then you see that it's just a complete rotation. And so in the Z plane, I will still end up with -1. So these two poles located at plus I or minus I will be located in the Z plane exactly as the same poles plus 2 pi plus 1I minus, or 2 pi minus 1I, okay? So to make it a little bit more evident, let's go to MATLAB and plot how the poles are located. So here I just make a quick code that I will also send you. And so what the code is doing is it's taking two poles, two complex conjugate poles in the S plane, map them in the discrete Z plane with the three different methods we've seen, okay? And the idea is to move this pole and see how moving the pole in the S plane will move the pole in the Z plane. So stable imaginary part growing, I guess this is the one I want to plot. So I hope it's going to work, should work. So here you can see that in the S plane, I take two poles, conjugate poles, and I'm just increasing their frequency with the same pulsation. And you can see on the Z plane that I've got three methods: the Tustin method, the matched pole zero method, and the backward difference method. So for the backward difference method, if the frequency is increased in the S plane, then it's just going close to 0 here. For the Tustin method, everything is going close to -1 here, as I already said, okay? And for the matched pole and zero method, something really interesting appears. So I will play it again in a second. That this here is the frequency, which we call the Nyquist frequency. So the sampling frequency divided by 2, so minus, and here the sampling frequency divided by 2. These two lines represent the sampling frequency divided by 2, okay? And as soon as a pole here is crossing this limit, then you will see that for matched pole and zero, you start here, then you increase in frequency. And when you arrive just here, you are at the same f over 2, okay? So just when you arrive at f over 2, then the matched pole and zero mapping, the first pole that coming from the top here is gonna start going in the bottom and kind of overlap with the other pole for previous, for smaller frequencies. So what I mean is that if I take a pole here, okay, it will be mapped exactly. So this pair of poles here will be mapped exactly as the same poles if I keep the same distance here and there as these two poles, which will have exactly the same mapping if I just take this Nyquist frequency and plot it again here. Then if I take exactly the same distance here, I will have also the same mapping. So it's just mapping to the, just these poles are mapped to the same Z poles, okay? Every time you have a kind of 2 pi revolution, so 2 pi times t over 2, which indeed corresponds to crossing the Nyquist frequency. So you can cross the frequency once, twice, 3 times, 4 times, and so on. And all the poles here, okay, so here and the complex conjugate here, will be mapped exactly as the same as all the poles here and the equivalent complex conjugates, okay? So if I play it again, you should be able to observe that if you look at the green dot, just when the blue dot on the left crosses the red line, dashed lines, then the green dot starts to overlap. And this is what's happening with matched pole zero, that every time you're higher frequency than the Nyquist frequency, you're going to overlap with the exact same location in the Z plane as a pole with the same natural or the same, not damping in this case, but the same real part in the continuous time, and the same frequency in the continuous plane, plus or minus a multiple of the Nyquist frequency. Okay, and this is why when you're discretizing the controller with backward difference or Tustin method, all the poles which are different in the S plane will be different in the Z plane. But with the matched pole zero method, all the poles that are different in the continuous plane are not necessarily different in the Z plane. Okay? Is this clear? Because this is really important to understand and to see that if I've got a transfer function like this, S plus A, S plus B, so let's call it G of S, then with matched pole and zero method, I can end up with J of Z, which here has two pole at infinity. So that will be located at -1. So here it's not the goal, but never mind, let's write it anyway. And on the bottom, I can end up with 1 plus Z square. So I can end up with the same pole in the Z plane for two different poles in the S plane. And this is just saying that A and B have the same real part, but some complex part, which are multiple of each other with the Nyquist frequency, so f/2. Okay. Also, now that this is open, I can quickly show you what's happening for real poles towards infinity. This one can be interesting. So here we're just taking one pole and we're putting this pole faster and faster. So it starts as an integrator. So it starts at 0 in the complex S plane is equivalent to 1 in the discrete plane. And then we increase it towards infinity, minus infinity. So we're making it faster. And you can see here that both the matched pole zero method and the backward difference method will map infinitely fast poles to 0 here, whereas the Tustin method will tend to map it to -1, okay? So what that means is that with the Tustin method, you will transform a continuous pole that has no frequency, okay? The continuous pole that's just a real part into something that has a non-zero real part and a kind of an angle, so kind of a phase. And this phase will be the maximum frequency you can have in the discrete time. So if you have only real poles in the S-plane, then using the discrete method of Tustin method will give you sometimes significantly different Z poles than using the match pole zero or the backward difference. Once again, which one is the best one? It's not possible here to say that one is better than the other one. It really depends on what you're discretizing and what your system is. Also, we can look at real poles towards 0. So here it will be the opposite. So if you're going to 0, in this case, all the three methods will do exactly the same. So if your pole is closer and closer to an integrator in the S plane, then you will be closer and closer to an integrator in the Z plane. So mostly you will converge to 1. Okay. So here you see really close to 0. All the three methods are mapping it to 1. Okay. And you can only see the green circle at the end just because they're just superimposing each other. If I zoom in, yeah, it's not even possible because for 0, a pole at 0 will lead to a pole at 1 for all the three methods, exactly 1. Okay, so if this is clear, you can also, you will have this code at home so you can play with it. Every time you're not sure how is it mapped from S to Z, you can just look at this code and see with the three method what's happening. Just a last example is if the S pole is it this one? So here the goal is to make it unstable, so it's definitely not this one, but I don't know where the one is. No, unstable pole, sorry, my mistake, it's this one. So if a pole is unstable in the S plane, you can see that directly Tustin method and match pole and zero method will predict or will place this pole in the Z plane outside of the unit circle, which makes sense. But with the backward difference, you still end up at the beginning, at least, with a stable system, okay? So we said that every pole that is stable in the S-plane remains stable in the Z-plane, whichever the method you're using, that's true. But for backward difference, if you're having an unstable pole in the S-plane, for Tustin and match pole and zero, you always end up with an unstable pole in the Z-plane. But for backward difference, it's a little bit more difficult, because remember that all the left half plane here that is stable is mapped to something here. So if I'm located, if I'm unstable in the S domain, okay, so if I'm on the right half plane, that doesn't necessarily means that I'm outside of the unit circle, okay? I can be in this region here where my discrete controller is stable, even if my continuous controller is not, okay? So this is not used. I mean, this property, I don't see any example where this property is used. That doesn't mean that you can design an unstable continuous controller and then discretizing with backward difference to make it stable. It's not always the case. You can see here that it's probably tangentially going to go here outside the unit circle. So it's just a general remark that stable poles are always mapped to stable poles in the Z-plane, but unstable poles using the backward difference method can lead to stable poles in the Z-plane. Is there any question regarding this mapping, this discretization of transfer function from continuous to discrete time? If there's no question, we can go to the third example. Indeed, the third example is really, really important. It's about aliasing. The idea is, let's say that we take any system we want, J of S, okay? So here, J of S, I guess it's given in the PDF. I don't even remember what it is. I guess it's just an integrator. Yeah, it's just one pole located at 3, but then we have a closed loop and JD is equal to 10. So whatever it is, I mean, we just have a transfer function. We have our zero order hold. We have our discrete controller. The controller usually is, all of this is defined at the controller. You got the sampler here. You got the controller transfer function in discrete time, and you got the zero order hold. And the idea is to say, okay, we will have 0 inputs. So if the disturbance is 0 at the beginning, then nothing is happening. I ask to add 0. The control input U here will be equal to 0. And so Y will be equal to 0. Okay. And now the idea is to add something, add some disturbance here. So we're just going to add just harmonic functions, just sine waves to start with, and to see what's happening if this disturbance has a frequency omega such that omega can be expressed as a frequency. So you know that omega is 2 pi f, so it's just f would be just omega or 2 pi. And what is f is bigger, much bigger, or just bigger than the sampling frequency, so then 1 over t, or also bigger than the Nyquist frequency. And so Nyquist frequency will be 1 over 2t, okay? So if the disturbance is faster than the sampler, basically, what is happening? Because the sampler cannot capture this special frequency. So if I've got a frequency of, if here my sampling time is, let's say 1 Hertz, and here my disturbance is 100 Hertz, what do I got in the output? Do I have 1 Hertz, 100 Hertz, something else? And this is what we will see now in this third exercise. So I've just been writing the, if I remember, yeah, the inputs a little bit differently. So instead of W, I just write it U to not confuse it with omega, the pulsation or angular frequency. For the Z here, yeah, it's lowercase z, so it's not a Z transform. Remember, it's not the Z from the Z transform variable. It's just Z because it's defined like this in the PDF. It's the disturbance. We have our sampling frequency that is 1 over 0.03, so it's 33 Hertz. And we also compute the Nyquist frequency somewhere. Yeah, So the Nyquist frequency is just sampling frequency divided by 2, and we're going to see in a second why we need this Nyquist frequency. So the system output should always have the same frequency as the disturbance if the input is 0, obviously, because we have a linear system. So here, if the disturbance, so if z is equal to sine of, let's say, 2 pi 1 hertz, for example, time t, then the output will be something, some coefficient a sine 2 pi 1 t plus a phase shift eventually. So plus phase shift, okay? So we know that from linear system theory that if the input, in this case the disturbance or minus the disturbance, has a frequency of 1 hertz, 5 hertz, 10 hertz, then the output will have 1 hertz, 5 hertz, 10 hertz, whatever. The question is, what's happening if the disturbance frequency, as I just said, is way bigger than the Nyquist frequency? And this is where aliasing will appear. And what's also happening by extension if it's strictly equal to the Nyquist frequency. We're also going to see that because it's a special case that can appear, and that is quite a big problem indeed. So here we end up with, if we try to analyze or to find an analytical solution from y, so y in the S domain and Z domain, so we can see that we have our plant here in the S domain, we have our so the plant is here, we have our zero order hole, then here I just wrote it in the S domain and then switch it to Z domain. So this will be my zero order hole if I just take this basically. And my plant is still 1 over S minus 3 and so on. I can find everything in the Z domain. And as you can see, the problem is that the closed loop depends on Z of Z, okay? Which is expressed like this. So it depends on the frequency of the disturbance, but it's not linearly dependent on the disturbance frequency. It's sine of the frequency divided by 1 minus something cosine of the frequency. So it's analytically, it's almost impossible to find a general or to generally find it easily what will be the frequency in y of z for a given fz, so a given disturbance frequency. So the question remains, what's happening if fz is way bigger than fn? So if my frequency in the sine wave of the disturbance is way faster than the sampler here, and the zero order hole, because it's the same, it's exactly the same sampling time, what's happening? And just to see if already some of you have some knowledge about it or some intuition, I will just share another poll. Okay, let me just find it. It's slide 38 something. Okay. So now I'm launching the poll. So the question is, what's happening if the disturbance Z has higher frequency than the Nyquist frequency of the system? So if the sampler is slower than the sine wave of the disturbance. The first proposition is the disturbance is filtered by the sampler, and so the output stays at 0. So here, for example, our Nyquist frequency is 33 divided by 2. Let's say that the disturbance frequency is 2 times the sampling frequency, for example. Then this first proposition is that the output will stay at 0, or always stay at 0. The second proposition is that only a frequency equal to the Nyquist frequency is present in the output. All other frequencies are filtered. So that means that when Z, the frequency in the disturbance Z is increased, then the output frequency will increase up to the Nyquist frequency. So if the Z has, if the disturbance has a really large frequency, the output will always have the Nyquist frequency. It cannot go faster, basically. The third proposition is that the sampler will transform this frequency into a frequency lower than the Nyquist frequency. So this proposition claims that if the disturbance has a frequency lower than the Nyquist frequency, then I will find this exact frequency in the output. But as soon as the frequency of the disturbance is higher than the Nyquist frequency, then the output frequency will start to decrease again. The fourth proposition is that the output will exhibit multiple frequencies, all lower than the Nyquist frequency. So once again, up to the Nyquist frequency, the disturbance frequency is exactly the same in the output. And when the disturbance gets faster than this Nyquist frequency, then the output will start having different frequencies. So not one, but multiple frequencies. And finally, because of the samplers, the model is nonlinear, and so the output will consist of varying frequencies all below the Nyquist frequency. So here the idea of this last proposition is that if the frequency of the disturbance is higher than the Nyquist frequency, then the output frequency will be a function of time. So instead of, for example, skip all here, if I've got my disturbance, where's my pen? If I got my disturbance C as a function of time, and I've got something really fast, okay, then this last proposition will say that in Y, instead of having one frequency that is really fast like this, for example, I will have a variable frequency. So probably something like this, okay? So that means that it's non-linear anymore. And so the output will not show one frequency for one frequency in the disturbance, but a varying frequency, so a frequency that will vary in time. I would just let you a couple of, one minute to answer. Here it's really like, do you already know what's going to happen? Have you already heard what will happen? Is it completely new? If it's completely new, you can just try to have a guess and what's happening. And this is exactly what aliasing is. Okay, so aliasing is anytime the input here, the E here, at a frequency that is higher than the sampler. Or even worse, it's higher than half of the frequency of the sampler, which is called the Nyquist frequency. If I share the result that now you can see, most of you said that the sampler will transform this frequency into a frequency lower than the Nyquist frequency, and that is the correct answer. So basically every time the disturbance will show a higher frequency than the Nyquist frequency, so half of the sampling frequency, then the output will show a frequency that is lower, always lower than the Nyquist frequency. The output frequency here, if I write Y as before, as equal to some coefficient A, oh, sorry, 8, where is my sign? A sine of 2 pi, let's call it Fy of t plus some phase, okay? A obviously is constant, phi is constant, okay, it's a linear system. Then I can always say that Fy is lower or equal, and we're gonna say that it's strictly lower, indeed, always lower than 1 over the sampling time, which is 1 over 2 times the sampling time, which is the Nyquist frequency, Fn, okay, which is also equal to the frequency of the sampling frequency, let's call it Fs divided by 2, okay? So my output, if my disturbance is a sine wave, whatever the disturbance frequency is, even if it's really larger than the sampling frequency, my output will always show one single sinusoid with one single frequency, okay? Of course, if my disturbance has two frequencies, then my output will show two frequencies, okay? So if my Z here is equal to a sum of sinusoid 2 pi f z t with some different frequency, my output will just be exactly the same number of sinusoid with frequencies always between 0 and the Nyquist frequency. And so if we look at our system now, I made a video. So on the top, let's play it at the beginning. So on the top, you have 3 signals. The blue one is a continuous disturbance. The orange one is the output. And the black one is the disturbance sampled. So if you remember, so here it's not strictly speaking Z, it should be minus Z because it's a feedback loop, but never mind. Just gonna write it here so that you all remember what it is. We got Z, then we got our sampler, okay? And then we got our system, so JC, we got our zero the whole, we got our plant system with GS or whatever, and then we got our feedback loop here, minus plus or here, and we just put minus whatever it is. And so the idea is Z in blue is a continuous signal here, and Z in black with dot is kind of Z star if you want, so it's the sampled version of Z. And what we'll see that the sampled version of Z here shows some frequency, and the frequencies in this sampled version will be exactly the same as the one in Y, obviously, because up to here, it's a linear system, can be approximated by linear system, remember. So what's happening if the disturbance is lower than the Nyquist frequency? You can see the Nyquist frequency on the bottom here, on the two graph on the bottom. This is the Nyquist frequency here, or multiple of the Nyquist frequency, okay? So if the disturbance is lower than the Nyquist frequency, for example, here it's 7.5 hertz, whereas the Nyquist frequency is 17 hertz, something like that, I don't remember, it's around 17, then the output will show exactly the same frequency, okay? And wherever the disturbance is between 0 and the Nyquist frequency, you can see that the output is always exactly the same frequency, okay? So this is perfectly known from linear system. It's exactly the same as in continuous time, and it's perfectly fine. Now the question is, what's happening if the disturbance frequency is equal to the Nyquist frequency? And if it's perfectly equal to the Nyquist frequency, so 1 over the sampling time, you can see that every time the sampler is taking a value, it's always the same value in the sinusoid, okay? So it's the signal that the controller sees is 0. And now the interesting part is that if we increase further the disturbance frequency, then you can see on the bottom, then the output frequency is decreasing now. And you can see that this is because if you try to connect the black dots, so it's done with the dashed line, then the frequency that enters the controller is much smaller than the frequency of the actual disturbance, okay? So let me just recap a little bit. First, it's the same frequency, then you arrive at Nyquist frequency at 0. And then if you further increase, then the frequency of the output will decrease up to 0 again when you have 2 times the frequency. So when you are at the sampling frequency. And then it will increase again, as you can see here. So here the output frequency is nothing else than the difference of the frequency between the sampling frequency and the disturbance frequency. So this frequency here, let's call it F, is the same as this one, okay? And then when you arrive at 3 times the Nyquist frequency, it goes to 0 once again, and then it starts to decrease in the output once again, okay? So you can see that wherever you are in the frequency, whatever frequency you have for the disturbance, the output frequencies just always map between 0 and the Nyquist frequency, okay? So to summarize, if the disturbance frequency is lower than Nyquist frequency, the output frequency is the same as the disturbance frequency. This is classical linear system. If the frequency is higher, if the disturbance frequency is higher than the Nyquist frequency and lower than the sampling frequency, so if you are in here, then you know that the output will still remain here, and it will just go here. It will decrease when this one is increased. And then if you are above the Nyquist frequency, so if you are between the Nyquist, if you are above the sampling frequency here, then you will still be here because it's the Fy would just be equal to the disturbance frequency minus the Nyquist frequency. Okay, so you can also generalize all this formula and you will find this equation here. There is a mistake here, it's 2Fn, so it's Fc minus f sampling, fs, okay, but whatever, it's not a big problem. If you take the general formulas here, what is it saying? That if the disturbance is increased, first the output is increased, then as soon as you cross the Nyquist frequency in the disturbance, the output frequency will go in the other direction. And then when you cross the sampling frequency, so 2 times the Nyquist frequency, then the output frequency will increase again. And then you cross 3 times the Nyquist frequency, so the output will decrease again, and so on. So the output, sorry, is just increasing or varying between 0 and the Nyquist frequency. And now to answer the question that we had to answer here. So here the idea is what would be the output frequency for disturbance frequency of 74.7 Hertz, for example. So 74.7 Hertz is this red point here. And so the idea is to say, okay, this red point is a little bit faster than the sampling time. So I know that the frequency that the system will see is the sampling time, it's the difference between this red dot and the sampling time here. And this difference is, sampling time is 33.3 Hertz. My disturbance is 34.7, so the output will be 1.4 Hertz, okay? If we look at the second point, we can make exactly the same analysis and say the output frequency will be this one here. So from the sampling frequency to the actual disturbance frequency. So it will be 49.3 minus 33.3, which is 16. But we can also see it from the other perspective. So we know that here our output frequency will be the Nyquist frequency. And so we can remove. So here we are at 15. It's 3 times the Nyquist frequency. We want 49.3. So we just take 15 minus 49.3, which is equal to 0.3 Hertz, okay? And we need to add to this is the difference, we need to add 1 Nyquist frequency. So 16 point, we need to remove this from 1 Nyquist frequency, because that 1 Nyquist frequency will be on the line, but a little bit before. So it's 16.3 minus 0.3, okay? And we can do the same construction for the blue dot, whether we say that we are at 0 here, and so we have minus 9.4 Hertz, or we can say that here we are at the Nyquist frequency that is 16.3, and we need to have 7.3, and it's or we need to remove 7.3, and it leads to exactly the same results. Is this clear? Also look at the blue line. The blue line here represents the output frequency as a function of the disturbance frequency. So disturbance frequency is it's this axis here. This is my disturbance frequency, and as you can see, my output frequency will increase to the Nyquist frequency. This one here is the Nyquist frequency in this axis here, and then it will decrease again, and then it will increase again and decrease again. Okay. Is this pattern understood by everyone? Because it's really important to understand what aliasing is. For example, in a system, if you have a disturbance here, imagine this is a real system that I want to control, and I've got a disturbance at 40 Hertz, okay? Then in the output, I will have around 7 Hertz. And this is really important because that means that I should not consider the disturbance being 40 Hertz, but I should consider that the disturbance is being 7 Hertz, okay? If I do the analysis in continuous time. So before moving to the question, let's first look at this MATLAB code. So I will also provide you this MATLAB code that can be quite handy to understand what's happening. So the MATLAB code is based on a Simulink that is right now opening. So in this Simulink, we have our disturbance here. That is some 2 pi times the frequency times the sine. It's just a sine wave, and then take the sum if you want to have multiple sine wave in the disturbance. And then this is just for the periodogram, for the plot of the periodogram, so which frequency I have in the disturbance and the output. And here is my system. So I've got my feedback loop here. This is just completely useless. I know what I've added it here. Never mind. I've got my controller that is 10, the order hold, and then the plant. Okay. So as we've just seen, if I take 10 Hertz in the input in the disturbance in this case, then you'll see that the output will show 10 Hertz. So we've already seen that. If now I add another frequency at the Nyquist frequency -2 Hertz, for example, then my disturbance will show two frequencies, one at 10 almost, and one at the Nyquist frequency -1, so it's or minus 2, so it's 14.67. And once again, in the output, I can see these two frequencies. So in the output, remind also that here's the frequencies do not have the same amplitude. This is because the plant is acting on these frequencies. And so obviously they are not all the same amplitude. Otherwise, I mean that the plant is just one. It's just a transfer function unique gain. And now the interesting part is if I add the same frequency +2, so Nyquist frequency +2, and what you can see is that now the disturbance shows one frequency that is 2 times more, also Nyquist frequency +2 Hertz, plus the one at 10 Hertz. And in the output here, we have now aliasing. So we have the same output for the 10 Hertz, no problem. But we have another frequency at 14.6 Hertz instead of 18.6 Hertz. And remember, this is because in the output, the frequency that should be here, okay, is just mirrored. Sorry. Come on. Okay, it's broken. So if I got the frequency here, it's just mirrored here to something inside 0 up to the Nyquist frequency. And here is the problem. If you're only given the graph on the right, this one, how could you know what are the disturbance frequency? You have no idea, okay? You can guess that maybe the disturbance show one frequency at 10 Hertz and then there's one at 14, but we've just seen that it's exactly the same as having a disturbance with frequencies at 10 Hertz and 18.6 Hertz. So when there's aliasing in the sample signal, it's already too late. You have no idea. You cannot recover which were the real frequencies and which were the frequencies coming from aliasing. Just to finish this example, if we add two frequencies, so Fn -2, so the Nyquist frequency -2 and Nyquist frequency +2, then you should have the alias, the Fn +2 frequency will have aliasing and will be mapped to Fn -2 as well. And so in this case, interestingly enough, one frequency is canceling the other. So here I've got 10 Nyquist frequency -2 here and Nyquist frequency +2. And in the output, I only got the frequency at 10. So frequency at 10 makes sense, no problem. Frequency at Nyquist frequency -2 basically is removed because there's aliasing that's appearing for the Nyquist frequency +2. And in this particular case, it's not always the same, but the aliased frequency is kind of destroying some important element from the disturbance, because here I can consider that my disturbance is important if it's below the Nyquist frequency. Imagine that it's an input. If the input is like this and you have a disturbance, so if the input is only this part here, this is what you want, and this is a disturbance, so at Nyquist frequency +2, then this disturbance would remove something from the input because of the sampling, okay? So this is really important. So is everything clear about aliasing, how it's appearing, how it's behaving? I can also add some really large frequencies. So Nyquist frequency +1, I can add a Nyquist frequency 3 times Nyquist frequency +4, for example, and everything will be once again mapped between 0 and the Nyquist frequency, okay? Now, if everything is fine, let's move to the last question for today. The question is when you're sampling a continuous signal with t = 1 second, aliasing may appear. So you've just seen that. Which is the correct statement? So there is only one correct statement. The first one is that using a low-pass filter on the continuous signal prevents aliasing by removing the higher frequency. The second one is that aliasing will appear only for frequencies higher or equal than the sampling frequency. Third one is that aliasing will show different behaviors depending on the sampling method. And the last statement is that knowing the sampling time and the sampled signal, it is possible to identify if aliasing occurred. So let me just share the poll once again. Poll is closed, and it should be this one. Okay. Now you should all see the poll and just please take some time to answer the poll again. So here the correct answer was the first one. Really quickly, second one, nobody answered. Second one, it was wrong because aliasing will appear at the not the I mean, it can appear if it's higher than sampling frequency, but it's more general, higher than half of the sampling frequency, which is a Nyquist frequency. This is fine. The C was aliasing will show different behaviors depending on the sampling method. This is just wrong. Okay, I mean the sampling method will affect the output, but not the frequency of the output. This is really important. If you take a signal like this, and you take a sine wave like this, and you sampled it, I shouldn't have done this. Like this should make it way faster. So if you take a really nice, not what I'm doing, and you sampled it, remember, then the sample method is just taking one value. If I define TS as being that large, I'm just taking one value every TS. So here probably is TS, here probably is TS, and so on. Okay. So first of all, different sampling method doesn't exist. There's only one sampling method. Sampling method is just taking a value at every TS second. And so aliasing is not dependent on the sampling method because it's only one sampling method, basically. Last one was knowing the sampling time and the sampled signal. It is possible to identify if aliasing occurred. I'm just going to show you that in MATLAB now. I've already said that before. If I show you this signal here, so the proposition was knowing the sampling time. So sampling time, I can give it to you, it's 0.03 seconds. And the sampled signal, so I can just plot the sampled signal plot. I just have no idea how it's called, don't remember. The sampled signal is called output T time white data. Should be this one. Out C or this one, probably this one. So this is my sampled signal. Just going to zoom in. The sampling time is 0.03 seconds. Here's the sampled signal. It shows some frequency at here. It's 10 hertz. Okay. Can you say if there is some aliasing? We're going to say no because it's only one sine wave at 10 hertz. So if we look here on the graph, what you will see is mostly this. So here it's not the sampled signal, it's the output. So it's the process sampled signal, but as our system is linear, it's just the same frequency as the sampled signal. So here one may say, no, here there's no aliasing, it's just one disturbance of 10 hertz. And in this case, it's true. Now, remember, if we add a signal at, for example, Fn plus 10, what will happen is that this frequency of Nyquist frequency plus 10, sorry, it's not plus 10, it's, yeah, 2Fn plus 10 will work. Don't want to count what it is. So here I'm adding another frequency at 43 hertz. Okay. And interestingly enough, I end up exactly with the same. So here the power is a little bit changed just because I've got two frequencies instead of one that are built to this 10 hertz frequency. But it's impossible to say if there's, it's impossible to say that here the frequency fz is equal to 10. Okay, I don't know. I know that fz is equal to 10 plus eventually something at the Nyquist frequency, 2 times the Nyquist frequency plus 10, but it can also be 4 times the Nyquist frequency plus 10, can also be the Nyquist frequency minus, so it should be 10 Nyquist frequency plus 10 should work also. It's not plus 10, it's 2 times the Nyquist frequency minus 10 will work also. So I can just demonstrate this if I'm not wrong. If you take 2 times the Nyquist frequency minus 10, it should also be located at 10 Hertz. Okay, and it's completely disappearing. So here now in the output, I've got nothing in the output, but the input has 10 Hertz and something else. So here, just to remind you that when you have a sampled signal, it's impossible to know if there were, if some aliasing appeared or not. So you cannot be sure of what frequencies were on the input signal, okay? And to avoid this problem, and this was the first proposition, if we go back to the PowerPoint, using a low-pass filter on the continuous signal prevents aliasing by removing the higher frequency, or the higher frequencies. There's multiple frequencies. And this is really important. It's called anti-aliasing filter. The most common one is a low-pass filter. So here I've got exactly the same setup. I will define one frequency at 10 Hertz to start with. I will disable the filter and I will add another disturbance as, let's say, the 2 times the Nyquist frequency plus 2, for example. So here nothing will be different. As usual, we have 2 frequencies and one is just get some aliasing, and so it's showing this really high frequency here in the output at 2 Hertz, 2 Hertz. And now I'm going to enable a low-pass filter. So if I open this second Simulink model, it's exactly the same as before, only here I've got the low-pass filter now. And this low-pass filter is a butterfly filter. You can look on Wikipedia what it is. It's just remember that it's a kind of a low-pass filter. And I will set this low-pass filter to the Nyquist frequency and filter order to 4. So this filter order will just tell you how fast it will damp frequencies above the Nyquist frequency. And if now I run this, I get rid of the aliasing problem. I've got 10 Hertz here. I've got something here that is barely not possible to see anymore because my low-pass filter is acting for all the frequencies above this red line, which is a Nyquist frequency. So in the disturbance, there's still a little bit of this frequency, but it's really damped a lot. And so in the output, I've got the frequency I want, 10 Hertz, and the other one also is damped a lot, okay? So if you want even a higher damping, you can increase the order of the filter, and now it will completely disappear. Problem is if you do that, then if you have a frequency that is really close to the Nyquist frequency, it will also probably, if I make like 0.1, so here this frequency is before the threshold of the filter, but already you can see here, it's completely damped already. Remember that this frequency here should be the same as the first one. So if I remove the filter in my disturbance, I will have 2 frequencies that almost have the same power. Yeah, it's not really power, it's periodogram, but never mind, they carry the same energy if you want. And if I add a filter, because my filter order is like really strong, if I got a frequency just before the filter, so I shouldn't touch it, it's already damped, okay? So this is the classic problem with anti-aliasing filter, is having a filter that is strong enough to really remove the high frequencies, but not so strong, so I still do not damp this frequency that much. And so usually you're not taking the Nyquist frequency, but you can also add a little bit, 2, 3 Hertz, whatever. And if you're doing it, then it's much better. You see the damping, it's much lower. But here I can still have quite strong aliasing because I moved my low pass filters threshold to something a little bit higher than the Nyquist frequency. Okay. So remember that every time you want to collect points, you want to measure something, The sensor usually is discrete time. Make sure that there is a filter, because if you don't filter the data first, you always know that there's a lot of disturbances with really high frequencies. In this case here, for example, you would probably see 50 Hertz frequencies usually, because the network grid is 50 Hertz. You can also see some multiple of 15 Hertz or whatever other frequencies. If you do not apply a low pass filter on the data before collecting them, or before collecting some sample of the output, then you will have some aliasing, and it can be really dangerous. Okay.
I have a question.
Yeah.
Where in the block diagram is the filter applied?
Here, so the filter, I just showed it. You got the input here. So here I've got Z. I can rewrite it differently. So I can say that this Z here is D is equal to sinusoid of 2 pi f1t plus 2 pi f2t. So I've got multiple frequencies in my signal, and here is the filter. So the filter, if I draw the block diagram once again, you got Z, then you got the sampler here. Let's do it like this. You got the controller, you got the zero, the hold, you got the plant, okay? Then you got the feedback, and here you will just add the disturbance and minus the feedback. Even if the disturbance in the PDF is here, it doesn't change anything. And so where you want to filter is before sampling. So here will be your filter, okay? You always filter the data before sampling the data. So usually you can have somehow a different setup. Usually when you have, so everything here is G, C, G, has your other whole whatever. In here you will have the reference, you will have the sampler, you will have the output. Usually the reference here is already, so this is completely different. Here's the reference U is already discretized. Usually you already know the reference that you want, you already discretized it somehow. And as it's a reference, there's no disturbance or whatever, because it's something you want to follow. And usually you make the filter here on the feedback loop. So from the output measurement, you make a filter, and then you can sample the output measurement here and bring it back here to sum plus minus as usual, okay? So you filter everything that you're measuring from the plant, okay? If the reference U is also measurement from the plant, you should also have a filter before any sampling, basically. Every time you got a sampling, you should have a filter in before to avoid especially some noise or whatever in the system. Also, I mean, it's not, here's the point, but if you look at two sinusoid with, so if you look at Z, like one sinusoid like this with an amplitude A, and another one like this with the same amplitude, this one will carry much more energy. So the one with really high frequency will carry much more energy. So that means that if you look at the periodogram here, one frequency that is here with a peak with the same amplitude here in the periodogram can mean, so it's just quantitatively speaking, but here's the amplitude of the frequency A is much bigger than the amplitude of this one, if I call it B, the amplitude here, okay? This is because a sinusoid will inherently always have higher energy density, let's say for high frequencies. So if my signal is just, if I just draw here equivalent of the system, I will have something like this. I will have a nice sinusoid. This will be the sinusoid here will refer to the frequency here, this one. And all the small here, can plug in red, all the small deviation here is a really high frequency that looks to have only a really small amplitude. So you can just say, okay, it's not a problem. Indeed, it is a problem, because even if the amplitude is quite small, in the periodogram, it will be really important. I mean, it will carry a lot of energy, okay? So that's why you always need to have a filter or make sure that there's no high frequency content in your measurements. Is it clear now?
Yeah, okay, thanks. And just to be sure, but the disturbance which has the higher frequency remains uncontrollable.
It's a disturbance. You cannot change the disturbance, but before putting it into the system, you can, I mean, here it's quite tricky because when we're talking about the disturbance in this example, if I go back to the block diagram, okay, I'll just here, stop. If I take here's the block diagram here that now you should be able to see, the disturbance is acting on the feedback loop. So the feedback loop here means that it's not the same disturbance as something like this, okay? The disturbance that will arrive here, I cannot control it. I cannot control this disturbance. I cannot filter this disturbance because it's acting on the plant inside the plant, okay? But the idea is when I'm making the measurements, I can say that there's the output y plus, so there's the y coming from the u, let's say y of u plus some y of the disturbance, okay? Which is, it's not always rigorously okay to write this, but this is the idea. The idea is I will take the output and I know that in the output y, I can only have frequency between 0 and Nyquist frequency. And so everything that is above here, I want to remove, okay? Because everything that is above needs or is, it can also comes from a disturbance here, okay? So here we're just using the filter in this place before key, and this filter already, we don't care about filtering it because it's 0, so it's really filtering the output. And as it's filtering the output, it's not filtering the output that has an important content, but it's filtering the output that shouldn't be here, okay? So we're not applying a filter in here. If I change the color, this cannot be, you cannot measure it usually. It's a disturbance, so it's directly acting on the plant. Sometimes you can measure it, okay? If you can measure it, you can directly filter the measured disturbance, and then you can work about it. You can also predict how the disturbance will affect the plant, whatever. But here you just consider the disturbance is internal to the plant. You don't know what it is. You just look at the output, and if the output shows some high frequency content, you just removed it, okay?
Okay, yeah, thanks.
And also worth to mention, this is just a model. So this would just be a model. So in reality, this J of S probably could show some high frequency, even if Z is 0. And so for the sake of the model here, if you keep this high frequency, then it can make your system unstable because some frequencies are kind of mapped into lower frequency and you don't want that. So it will not make it unstable, but it will make it, you will not follow the input exactly as you want, okay? Because, for example, really trivial example, if u is kept at 0, then here the output u that is not coherent to have 2 times u, by the way, I just realized it now. So let's say it's uc, u from controller, then u from controller should always be 0. It's obvious. But during the measurement here, you will have measurement noise. So the output will look like this. This is my output. And so the controller here, this will lead some aliasing, and to the controller you see here will be non-zero. And if you see is non-zero, then instead of just having some white noise in the measurement, you will start having something like this, and it will be worse. That means the output is not following 0 anymore. And this is just because you're not filtering before sampling. Okay. Now just want to make a quick conclusion, and then I can answer further question if there's some. So we've seen today a discrete controller with unknown parameters. We've used a jury stability test and W transformation and Hurwitz test. So that was last week. And with that, we were able to design a controller pulse transfer function. So just a controller transfer function from a discrete controller. So here the idea was, I know what the discrete controller is. I'm just finding its parameters to be sure that the system is stable. Then we find a continuous controller, which is design a continuous controller in continuous time with classical method. And then we discretized it. And we've seen mainly 3 methods: finite difference method, Tustin method, matchable zero mapping method. And finally, we've seen what aliasing is, how it can appear, what it is, and what we can try to remove aliasing, or at least damp the high frequency content of my output that shouldn't be here. Okay, so I hope that this is quite clear for everyone. You will also have the MATLAB code, so you can play around with it and see what's happening. And now, do you have any question regarding this session or the sessions before, or general question, remarks? I don't know. If you don't have any question, you will have, as usual, 2 weeks starting from now to do the homework session 4. Homework session 4 is not about aliasing, if I remember well. It's just about some control. So first, it's finding the parameter of a controller. It's not the controller, it's just directly the closed loop denominators, the characteristic polynomial. And the second problem is just discretizing some controller. You can reuse the MATLAB code, Simulink code, and just comment what's happening. And that's pretty much all from my side for today. Do you have any question? Or was everything perfectly clear?